You can find the link for the talk on the website, and Ioannis will be talking about our universal criteria of analogical reasoning hopeless. And you're all invited to join us for this talk. Again, the Zoom link is on the calendar on the website. You can also find some a short interview of Ioannis that we put on the website if you're interested to know about him. The next and last lunchtime talk will be on Friday next week here at the center. It's going to be the last talk of the semester and will be given by Arnon Levy, the senior visiting fellow at the center, who will be talking about a critique of the argument from inductive risk. So more of you, the title has changed since Tuesday. No? It's Tuesday? Since Tuesday. I think I mentioned you talk on Tuesday. I gave another title. So, but something
is it a better one? Or?
It's the same topic, broadly understood, but somehow it doesn't sound like the same title. In any case, so Arnon will be talking about inductive risk next week on Friday here at the center at noon. And if you are planning to apply to the center next year, the deadline for both the postdoctoral fellowship and the visiting fellowship is December 10th. Today, it's my great pleasure to introduce Dan Nicholson, who is currently a visiting fellow at the center. He's assistant professor of philosophy at George Mason University, so not too far from here. He got his PhD in philosophy from the University of Exeter. He also has a master in biology. In the molecular and cellular biology from the University of Bath. He has been, before going to George Mason, he was at other places such as the Konrad Lorenz Institute in Austria. He is quite well known, in fact, very well known philosophy of biology for his work on organism. He has been pushing the idea that we should think of living creatures as full organisms. We should not reduce them to mechanisms or machines. In fact, one of his paper studies published a few years ago with the title "The Concept of Organism in Biology" is actually an extremely well-cited paper on this topic. He's also the editor with John Dupré of Everything Flows Toward a Processual Philosophy of Biology, where he defend the view that we should have a process view in contrast to a thing view, one might say, of organisms. And he's been doing a lot of work in the history of biology, the philosophy of biology, and also he has published quite a bit in scientific journals, recently in the Journal of Theoretical Biology. And it's been really good to have you this semester. Thanks for coming. All right, floor is yours.
All right. Well, thanks, Eduardo, and thank you for coming. I'm really, really excited about being here and having the opportunity to present to you what I've been working on. Just set up my phone. So what I'm taking a little bit of a risk in presenting something which is completely new, but I think it's also, I guess, more exciting because it means I can really benefit from the Q&A. So I'm really looking forward to hearing what you make of what I'm going to present to you today. This is a very much work in progress. It's a new project. And I guess I should apologize for the extremely long title. This is by far the longest title I've ever used in a talk. I guess the reason for it is that I'm trying to bring together a number of different discussions or areas of scholarship that usually don't have any contact. Okay, and as I was thinking about how to do this sort of synthesizing project, it occurred to me playfully that I could think of it as a sort of a play, or sort of or opera or something with several acts, right? Because you have a number of characters that recur, right? And which I'm going to be presenting to you. I should say, of course, this is going to be a bit of an HPS talk, not so much a Phil Sci talk. I figured it would be a good opportunity to do that, given that many of you do integrated HPS. But there should be a lot of interesting sort of philosophical questions and lessons along the way that we can pick out and dissect. So, the title, what is it trying to capture? Well, maybe start with two revolutions. Okay, so the project is looking at really the relationship between biology and physics, okay, the dialectic between biology and physics in the 20th century, okay? And within that dialectic, there are two really interesting events, okay? So these two revolutions. One which seemed inevitable. It seemed like it was going to happen. It was bound to happen. It was imminent, and yet it didn't happen, okay? And another that seemed to start in one way and ended up unfolding in a completely different way, okay? And this very first revolution, which is shown in the first part of the title, the new physics behind the old biology, refers to this organicist movement in the interwar period, which I'm going to be discussing, which essentially tried to draw on the new developments in physics, revolutionary developments in physics, to develop a new biology. And as I say, this revolution didn't happen. It was bound to happen, and it never did. And the second, the old physics behind the new biology, is a reference to molecular biology, the molecular biology revolution, okay? Which, despite being, of course, one of the most successful events in the 20th century, by scientific events of the 20th century, unfolded in a way that was quite different from the way many people expected it to. Okay? So I have 3 acts here because I'm gonna tell the story in sort of 3 episodes, okay? So here, before I start, I figured I'd mention there's a lot of work, a lot of people have written about the relationship between biology and physics, a lot of historians and biologists and philosophers. These are 2 epigraphs which I think can help us sort of set the scene. Ernst Mayr, in his last book, wrote that hardly any of the great discoveries in physics of the 1920s had any apparent effects on biology at all. And Ernst Mayr, writing here at the age of 100, having lived through the whole 20th century, seeming to suggest that there's no reason for any biologists to concern themselves with what's going on in physics, because it didn't have any effect. Okay, and the late Evelyn Fox-Keller, writing in 1990, just expressing the fact that for a long time historians of biology were very much concerned with this question about what physics contributed to molecular biology. Okay, and so this is what is being expressed here over and over again. Returns to the question of what is it that physics contributes to molecular biology, and we still have not arrived at a satisfactory answer. That was 1990. 30 years later, I'm going to try to show you that we still don't have a good answer. There's still a lot to think about here. Okay. All right. So here is the outline, the acts. Okay. So I said there will be 3 acts, and I'm going to start with a little prelude, and I'm going to end with a little coda. Okay. So the first act is waiting for the organicist revolution that never came to pass. Okay. The second act, the anti-reductionist spark that triggered the reductionist revolution. And the third act, how quantumist biology failure enabled molecular biology's success. Okay. And what I'm going to do is I'm going to offer you a sort of, another motivation for structuring things in this way is that there seems to be a sort of an irony and sort of an ironic conclusion at the end of each of these. Okay, so I'm going to conclude my exposition in each of these 3 with some sort of contradictory, ironic conclusion that hopefully we'll have a chance to again discuss later. Okay. My prelude is set to set the scene. Starting point is Copenhagen 1932, and at the end I will try to in some way connect what I've presented to the present. Okay, so what's the relevance of how can we update this story, given that the story is very much a 20th century story or a 21st century update? Okay. All right, so let's begin with the prelude. So why Copenhagen 1932? Well, that is the place and the time, August 1932, when Niels Bohr presented this very famous address at the Second Congress of Light Therapy in Copenhagen, where he presented for the first time his views on biology. Okay, so he had 5 years earlier proposed his principle of complementarity at a lecture in Como, and since then, in fact, from the very beginning, he had the idea that this notion of complementarity that was supposed to provide sort of a foundation for what came to be known as the Copenhagen interpretation of quantum mechanics could also be used in other very different contexts. Okay, so that's what he presents in this Light and Life address, where Bohr says that biologists face a situation with life that is analogous to the one physicists face with atoms. In both cases, we require two mutually exclusive, yet jointly necessary descriptions. Okay, so in the case of biology here, of course, what we're talking about is the sort of old long-standing mechanicism, vitalism debate, or the antithesis between Kantian terms between mechanistic and teleological explanations. Bohr is basically suggesting that any sort of mechanicist analysis of an organism has to be complemented by a description of the agential or purposive character of an organism's living state. Okay, each of these two descriptions of a living system is autonomous. None can be reduced to the other. So he says, just as in physics, it is not possible to fully account for atomic phenomena without experimentally interfering with them, so in biology, any attempt to trace the individual atoms making up the organism is incompatible with keeping it alive. You've got this similar epistemic predicament that when confronted with an organism, you can either try to track every single atom that makes it up to explain the constitution, but in doing that, you're going to kill the organism, so that you have there's sort of an inevitable experimental interference. So that's the analogy with physics. So here's a quote from the English version of the address. It was actually published in 3 languages, in Danish, German, and English. He says, we will doubtless kill the animal if we try to carry the investigation of its own so far that we could describe the role played by single atoms and vital functions. In every experimental living organism, there must remain an uncertainty. He uses his words carefully. Of course, this is a reference to the uncertainty relationship in physics, as regards the physical conditions to which they are subjected. The minimal freedom we must allow the organism is just large enough to permit it to hide approximately. Basically telling us that there's some sort of limitation in our understanding of life. Okay, and because there's a limitation, we ultimately can't explain life. We have to take it as a given. We have to assume it as an elementary fact, as it were. A starting point that any physiologist assumes to begin investigation. And there's again an analogy with the quantum of action, which Bohr says appears as an irrational element from the point of view of classical mechanical physics, but forms the foundation of it. Right. So his appeal to so you can ask where this Bohr's interest in biology come from. Okay. Well, it seems quite clear when you look at his at Bohr's writings from 1927 onwards that, as I said, from the very beginning, when he introduces the notion of complementarity, he's thinking about how he can clarify what he means by drawing analogies to other areas where there seems to also be a complementarity relation. Okay, so he very quickly, already in 1928, is discussing the idea that there may be complementary descriptions of life and also complementary descriptions of consciousness. You can very quickly and easily see how that would work, right? So you can either the act of thinking interferes with the thing that you're trying to understand. So there's also a complementary relationship there. But it seems to be in some way motivated by the desire to make clear what he meant in physics. Okay. But there's another very interesting aspect when you look at Bohr's biography, which is that he was born in a household where a lot of discussions were happening about biology. His father was a very prominent physiologist, Christian Bohr, known for the Bohr effects and respiration. At one point, Bohr talks about how, as a child, he remembers his father discussing with colleagues, including the New Kantian philosopher Harold Hoofding, the conceptual foundations of the life sciences. Okay? And Christian Bohr himself, born in 1858, so we're talking about someone who was writing in the late 19th century. Himself was seems to also trying to steer a middle way between mechanicism and vitalism, okay, in his work. So he accepts the practical importance of deterministic physical-chemical principles, while at the same time noting that in any physiological experiment or any physiological explanation, we need to keep the whole organism in view, right? So this is going to be important later. All right, so that's just the prelude. Okay, so we have that sort of setting the scene with Bohr giving this address where he provides his first comprehensive attempt to apply his complementarity principle to biology. Let's then begin with the first act. Okay, so what's organicism? Organicism is basically an intellectual movement that came to prominence in the early 20th century. You can think of it as basically a standpoint, the standpoint that attempts to pick the best of both worlds from the two sort of long-standing schools of biological thought in physiology, embryology, and so on, mechanicism and vitalism, by essentially trying to argue that neither is sufficient, neither in fact alone is satisfactory, and basically you have a number of authors in different countries that come together, that engage with one another's work, that collaborate, that discuss, that co-author, and come together to basically develop this new sort of philosophy of biology. So here are the actors of this act. These are perhaps the most prominent authors. There are many more, of course. So I won't go through all of them. John Scott Haldane may sound familiar because, of course, he was the father of the more famous J.B.S. Haldane, one of the founders of population genetics. J.S. Haldane was a very prominent physiologist in his own right. Edward Stuart Russell was a behavioral scientist. J.H. Woodger. So I don't know if not all these names may sound totally familiar to you, but the point is that you have people from around the same time in different countries. So 2 Scots, 2 Brits, Austrian and a German. But of course, there were advocates of organicism in the US and in Italy. I'll mention some others. Okay, and the point is that these people were not just randomly writing about the biological theory. They knew each other, they worked with one another, they responded to one another. There was actually a discourse. There was an organicist discourse. And also the term organicism is not a historiographical label. It was a term that was actually appropriated by the historical actors themselves. Imposing this idea on them. J.S. Haldane is the first one to use the term organicism to refer to his work. And he does so in order to distinguish himself from people who are accusing him of being a vitalist, because he's projecting mechanistic machinery of the organs. So as I already mentioned, if you think about what they stood for, the most obvious thing that one can say is that they stood for the resolution or the dissolution of this long-standing conflict, which arguably goes back to Descartes, if not earlier, between this mechanistic and vitalistic ways of thinking about ontologies of living systems. Okay? Here are some quotations from some of these actors to show you how they think about their position. Joseph Needham actually is an interesting character because he originally was very much a mechanist, but he ended up becoming convinced through discussions with J.H. Woodger and Waddington, another author that perhaps is well known of the importance of organism. He says that organism combines the insistence of vitalism on the real complexity of life with the heuristic virtue of the mechanistic practical attack. Here's Ludwig von Bertalanffy. Organisms vindicates the autonomy of life, which is denied in the mechanistic conception, and remaining a metaphysical question mark in vitalism. Okay, so we're talking about people who refuse to accept any sort of metaphysical explanations for biological complexity, who recognize the importance of experimental methods, rigorous analysis, right, physical-chemical approaches, but at the same time recognize that if we want to understand what life is, you need to think of organization, you think of the system, you need to think of biological phenomena in the context of the system to which they belong. Okay. Right. So just to show you that this was a movement that had quite prominent during the period. There's a very nice review article. Some people think the philosophy of biology started with, I guess, David Hull, Michael Ruse, Ken Schaffner, Bill Wimsatt in the late 60s, early 70s. It's nonsense, actually. There's been people, obviously, there have been people working on philosophy of biology since Aristotle, but even the term philosophy of biology was used in the early 20th century. There's a review article by Needham called Recent Developments in the Philosophy of Biology from 1928, so almost 100 years ago, where he says, the standpoint of organism is probably, it's an important factor, something force to be reckoned with, or something we need to consider when we're considering the philosophy of biology. Here's a book by William McDowell from 1938. It's just a survey of biological theories, as it says here, where he says there's now a large number of biologists who give addition to what is called organicism, or the organicist, or organism, or organism doctrine. Again, just to show you that I'm not projecting my labels onto these people. Okay, so there's organicist discourse. What did they maintain? Of course, there was a lot of heterogeneity. They disagree with one another. That's why it was discourse, but you can identify certain things that they stood for. Okay, one of them is the idea that the organism is the sort of the central category in biology, central concept, right? So here are some quotes. So Russell says the organism is the starting point of all biological theorizing and the unit to which all biological concepts and laws must relate. Okay. Bertalanffy draws an analogy with physics and says the concept of the organism is as central to biology as the concept of energy is to physics. Okay. The idea that organization is very much the exponendum of biology. You know, if we want to advance in our understanding of life, we need to take seriously organization. That's something, again, that you find all of these people defending in some way, rejecting the idea that there's a matter of life and focus and trying to bring sort of the focus on relations rather than matter. You know, Needham has a whole paper on 1932 of just called, you know, organization is the central problem of biology, but it's a notion that recurs in many of the other methods. There's also a rejection of the machine conception of the organism that usually traces back to Descartes, which has been a very prominent and influential way of thinking about life for about three and a half centuries. You have the different organicists defending or rejecting that view in different ways. Which is saying that it's put us on the wrong scent. How long are we to persist in refusing to look at sheer facts in the face? But Bertalanffy is saying we shouldn't really talk about a machine theory, but just a machine fiction at most. And also, in fact, many of them, actually most of them, defend a processual account, a processual understanding of living systems, right? Grounded in biology. So thinking, okay, you know, the metabolism and development gives us good reasons to not just reject the machine view, but also accept dynamic view. So here are some quotes to that effect. Woodger talking about an organism as an event. It's the first one of the first authors to talk about temporal parts before the metaphysicians were doing so, already in 1929. Talking about this temporal differentiation of the organism. It's kind of interesting. These are massive books, by the way, 500 pages, big treatises, papers. Russell talking about how we commit, you know, a fallacious abstraction when we take the adult organism to be the organism, right? The organism is actually the life cycle, and anything that you are looking at is only a temporal part of the life cycle, right? So again, very dynamic. And of course, this should remind you a little bit of Whitehead. It's not a coincidence because many of these organicists were very much inspired by Whitehead, but not by the Whitehead of process of reality, not by the heavy-duty metaphysician, but actually from the mid-career Whitehead, the mid-20s, the Whitehead who wrote Science in the Modern World, Concept of Nature, because in those books, Whitehead was essentially grappling with the crises in physics and suggesting that we needed a new way of thinking about nature, a way of thinking about nature where physics will no longer have the authority to dictate how we should think about to provide the concepts with which to think about the world, right? And many of these organicists found this very, very inspiring. So here are just some of the philosophical implications that Whitehead drew from the revolutions that took place in the turn of the 20th century in physics. One, and these are of course things that the organicists wrote about and thought about, the erosion of mechanicism and materialism as a natural philosophy, which has prevailed since the scientific revolution. The demonstration that everything in the world is somehow connected to everything else, that there are no absolute boundaries, no isolated parts. The abandonment of strict determinism and predictability in nature, possibility of a role for mind in nature, and the restoration of the human observer to a central position in natural philosophy. These are things, of course, which seem to be read out from the developments in early 20th century physics. But obviously, all of these things have implications, consequences for biology. Okay? So let's give you a couple of examples. Okay, so here is Russell in his 1930 book, The Interpretation of Development and Heredity, probably the most ambitious attempt to criticize Morgan's sort of chromosomal theory of the gene, to actually defend a sort of an anti-realist view of the gene in 1930, using a whole battery of arguments in history and so on and so forth. So here he is. Actually, this is in the chapter on the organism point of view. Probably don't know if you can read it, but he's actually beginning by talking about the collapse of materialism. And very quickly, of course, he starts, Whitehead comes up. So here is a quote of Whitehead. He says, materialism has failed even in physics, right? Where it had its most striking triumphs, they're proving inadequate. And here's a quote from Whitehead: the progress of science has now reached a turning point. The stable foundations of physics have broken up, and also for the first time, physiology is asserting itself as an effective body of knowledge, as distinct from a scrap heap the old foundations of scientific thought are becoming unintelligible. All these concepts, time, space, matter, material, ether, electricity, mechanism, organism, pattern function, all require reinterpretation. We are basically starting from scratch, as it were. And we are in a situation where physics doesn't have the upper hand, right? Biologists for 3.5 centuries have had this sort of physics envy. This is sort of a very characterized view, where they assume that the way to become respectable as scientists is to basically import and adopt the concepts of physics. What was so exciting for these people at this time was that for the first time, that didn't need to be the case. You had Whitehead and many others basically saying that this was not going to work. In fact, he said, this is another quote, the appeal to mechanism on behalf of biology was in its origin an appeal to the well-attested physical concepts, but at present there's no such system of concepts. So no, we need a different framework, a different perspective. It's also a little footnote here to basically discussing the collapse of determinism. It's a reference to Arthur Eddington here. There's a lot of references to physicists in these works, where basically determinism has had to be dropped out altogether in theoretical physics, and this is implications also in biology, right? And and so what Russell does in this chapter is say, well, given this situation, what we now have to do is to look around for a new set of concepts which will enable us to establish biology on a footing of its own. The new concepts must, of course, link with those of new physics on the one hand, and Russell himself is advocating this sort of psychobiological view. He thinks that that's actually one of the missing aspects in biology. So for him, psychology is also going to provide a foundation. But anyway, just to give you a sense of how some of these discussions took place and followed. Here's another example, very nice example from Woodger in his big magnum opus Biological Principles from 1929, where the preface, the very first page when you open the book, begins with this wonderful analogy of a crab. He says, this is the first sentence, modern science may be likened onto a crab, which has grown too fat for its shell. The process of ecdysis is slow and painful. The old shell, which is mature and hardened for some 300 years, is done good service. That's, of course, the old shell, the mechanistic, deterministic, reductionistic view. No wonder the crab is loath to part with it. But it has already begun to crack and some bits have dropped off. What are we going to do? What is to be done? Should the crab go on getting fat and take no thought for the raiment of the morrow, or should it resolutely face the situation, heave off the remains of the old shell with a sigh, and set about making a new one in earnest? There's a lot of uncertainty about what's going to be the texture of the new shell. So it's very much poetically expressing this sort of the zeitgeist at the time. The evil day cannot be delayed much longer, and if it's put off too long, the process of growth may suffer. And then he explains the data of the natural science constitutes the meat here in this analogy. The shell is the general philosophical background that's become obsolete. And so on and so forth. And just draw your attention to this sentence here. So far, this revolution appears to have had little influence on biology, but has been confined to physics. Changes in the foundations of physics, however, may be expected sooner or later to concern biology. Right? So again, another example, someone in the interwar period suggesting that the future of biology was very much linked to the new physics. Right? The new biology is going to be based on the new physics. Here's my final example, Bert Lampi's Modern Theories of Development. There was actually an English translation of a German book, 1928. And look who translated it and adapted it. Woodger told you who these people knew each other, work with each other. Nice thing in the preface here is that he's actually referring to other of the organicists who basically had written similar books and saying how this correspondence and the similarity in all these works is a sign that this way of thinking, the organicist way, is in the air and is forcing itself upon the attention of independent authors. Okay? And I'm not going to read it, but this is the first chapter where, again, like Woodger, Bert Lampi begins with this idea that there's a crisis, right? And what is to be done, right? There's a crisis that, it's a historic spectacle. The remarkable developments which have been recently coming on to fruition in physics suggest a totally different interpretation of what we should make of this crisis. And so it's really much an opportunity. It's an exciting opportunity to rethink the foundations of biology as well as physics. So in other papers, here's one in German from 1927, Bert Lampi specifically talked about the meaning of the transformations in physics for biology. Here's a quote from another book, which I think is gives you a taste also of how Bert Lampi, for example, was thinking about the analogies and the importance of modern physics. He says, in modern physics, there's no matter in the sense of rigid inert particles, not anymore, but rather atoms are node points of a wave dynamics. So in biology, there's no rigid organic form as a variable process of life. Rather, there's a flow of processes manifesting itself in a parallel system. So there's an appeal to the new physics to defend the biological, the new biological position. And there are a number of interesting calls that that organicists make. So this one by Needham, where he says modern biology, I mean, is basically complaining, right, that the revolution still hasn't happened. Modern biology is in a position totally different from physics. For although the latter have undergone revolutionary changes since the beginning of the century, the former has not. Biologists are still following the ideal set for them in the great days of the last century. And T.H. Huxley, Darwin's bulldog, was brought back to life. He would be as much at home in contemporary biology as he would be at sea in contemporary physics. Woodger, being more characteristically blatant, says, well, if we are to make use of physics in biology, let it at least be modern physics and not the warmed up corpse of Victorian speculation. Again, showing that this long-standing relationship between biology and physics, which is often construed in terms of reduction, has to be rethought. Okay? There is also a very interesting event in the Second International Congress of the History of Science. The event that happened in London, 1931, a year before Bohr's Light and Life, brought together actually many of the people that I've mentioned in the same session, and noticed the title of the session: Historical and Contemporary Relations of Physical and Biological Science. That was the topic. Okay, you can actually see the proceedings, right? And what you find there again is the appeal to physicists. So here's Woodger, referring to a quote by Max Planck. I won't read all of it, just to show you here. He says, basically saying that the concept of wholeness is going to have to be introduced as well into the field of physics, into biology, in order to enable us to understand and formulate the laws of nature. Planck saying that, okay, we need wholeness in physics and in biology. And then a bit later, cheekily says, he refers to this quote, because obviously he was present when Woodger used it, and he says, well, if we accept what Planck is saying, the conclusion is that mathematical physics can be regarded as a backward branch of biology. Why would he say that? He's saying that because biologists are used to thinking about wholeness. They've been thinking about wholeness for centuries. It's the biologists that have, in some sense, the upper hand. Okay. Okay. So what does all of this have to do with Light and Life and Bohr? Well, there is actually a very interesting connection between J.S. Haldane and Niels Bohr, in that J.S. Haldane visited Bohr's father, Christian Bohr, in the late 1890s, in the early 1890s. And actually developed, also became friends with Niels Bohr. And there seems to be, real sort of correspondence and convergence in the views that Haldane is defending philosophically, and the views that Bohr is putting forward in these addresses on complementarity. Okay, he talks about how this was going to not be understood in physical terms. And he even talks about life as an irreducible fact. He calls it the axiom of biology. This is a book called The Philosophical Basis of Biology. So there's a very interesting situation here that Bohr, who was one of the catalysts for the revolution in physics, was himself influenced, apparently, seemingly, by some ideas that were being developed by his father and some biologists in Britain. He even had suggested, and this is from his book Mechanism of Life and Personality, that this idea that you can't trace the atoms without destroying the animal, this is something that I've actually found being uttered by Haldane 20 years earlier. So this is, and this hasn't really been recognized so far in the literature. I mean, there's been some sort of indications that J.S. Haldane might have been influenced, but not so clear. So I think this is quite interesting. Haldane actually notoriously already in 1909 suggested at the end of an address that thinking about the relationship between physics and biology, that if there would ever be a meeting point between biology and physics, and one of the two sciences would be swallowed up, the one that would be swallowed up would not be biology. Okay? This came to be known as sort of Haldane's prophecy, Haldane's dictum. So here's Joseph Needham in his book Order and Life, which, by the way, was dedicated to the Theoretical Biology Club, which brought together many of these organicists. This was 1935 or 1936. writes the celebrated Haldanian dictum, this one, is supposed by many apocalypse to be on the verge of fulfillment. Needham is here being a little bit skeptical. And who is he thinking about? Well, he's thinking about someone I haven't mentioned yet, which is Adolf Meyer-Arbig. This is someone based in Hamburg, who actually really ran with this idea that Haldane was putting forward, that the way to think about the relation between biology and physics is not even one of mutual interdependence, but one of reducibility, but the physics will be reduced to biology. So how does that work? Well, it works by what Meyer-Arbig calls holistic simplification. The idea there is that that we should think of biological principles just being more general than physical principles. And that because they're more general, you can derive the simpler principles from the more general ones. So it's just turning the whole argument of reduction of centuries on its head. Okay, so here is, he in fact translated into German, some of Haldane's works. So here is probably the most important work, and then 34 ideas, an ideology of biological knowledge, where essentially he tries, inspired by Haldane, tries to do exactly what I just said. He tries to think of which physical concepts we can derive from physics, from biology. Okay, so he says, for example, this is a very short summary. He does this over many pages. Entropy can perhaps be regarded as a special case of biological disorganization. The principle of relativity is perhaps derivable from the relationship between organism and environment. And the uncertainty principle can be thought of as a consequence of psychophysical relation. Now, I'm not suggesting that all of these claims were compelling, the watertight, but that this is perhaps on the more radical end of the proposals that were being put forward. So what happened? What happened to the world? The revolution never happened, as I said. It never did. There was a move by Joseph Needham to try to institutionalize organicism in Cambridge. He was based in Cambridge, and he spent a couple of years writing some proposals to the Rockefeller Foundation, which had decided basically to fund new work in physics, in biology, and so he did this. He provided this was a very long memorandum on an institute that it was going to be on mathematical, physical, chemical morphology. That's the term that he used, where it would have a division for each member. This is from the archives in Cambridge. You can't really read it, but you have all Bernal and Waddington and Woodger all in charge of different areas of this hypothetical, institute that never. And of course, the idea there was to foster interdisciplinary engagement on the problem of organization. So before that was the main problem. But in the end, it didn't happen. Warren Weaver decided not to fund it. There were a number of reasons. Some of them had to do with the fact that many of these people were political radicals, were Marxists, but also having to do with the sort of the ontological assumptions that they were bringing to the table. And in the end, of course, Weaver helped promote, if he didn't coin the term molecular biology, and of course the Rockefeller Foundation played a huge role in ensuring that in financing the work that led to the revolution when it finally came, which was not the organicist revolution. Okay, in fact, just to mention one book on this, on the Rockefeller Foundation and the rise of the new biology. Notice the term new biology here. The new biology, when it arrived, was not based on the new physics. It's actually based on the old physics, 19th century physics. Of course, there was some information theory and there was cybernetics, and of course these were new developments, but for the most part, the general view of nature that you have people defending within a molecular biological framework is the old view. And here is another physicist just noticing this, David Bohm. It does seem odd that just as physics is moving away from mechanicism, biology and psychology moving closer to it. If this trend continues, we may find that scientists are regarding living beings as mechanical while supposing that inanimate matter is too complex to be understood by humans. Here's another one from Carl Rose, a very well-known microbiologist. Biology from the century was in the strange position of having to contort itself to conform to a worldview and mechanicism that 20th century physics was simultaneously in the process of rejecting. In a metaphysical sense, molecular biology was outdated from the onset. So that's that's sort of the ironic conclusion. So what happened to organicism? Very quickly, the older people, the older generation died. Of course, J.S. Haldane was eclipsed by his more famous son, also very important sort of Marxist science popularizer. E.S. Russell died in 1954. J.S. Woodger became obsessed with axiomatization and logic, became the translator of Tarski. He had an affair with Carnap's wife. He became very much sort of in that possibility. Needham had two Chinese PhD students visiting in 1936 and decided to learn Chinese and went on to become the world foremost authority on the West on the history of Chinese civilization. Bertel Amphi became interested in his theoretical. He tried to expand his theoretical biology to all kinds of systems. And what did he do? He developed general systems theory. You know him. You probably know him exactly for that, for his general systems theory. And Meyerbeek, well, unfortunately, stayed in Germany during the war and had a lot of trouble rehabilitating himself after. I won't go into these. Are super interesting, but don't have time. Okay. The point is that it's just a sequence of unfortunate, accidents that this movement has basically been erased from the collective memory. And also, I don't have time to discuss this either, but there's also some sort of political maneuvering that was going on the part of people like David Hull and Michael Ruse when they started, when the first text was from philosophy of biology, where they essentially tried to wipe the slate clean and argue that there was nothing important that had been done before they arrived. Okay, so this has really damaged the field because it meant that people, basically several generations, have been oblivious of this, and only now people are beginning to pay attention. Okay, I spent a lot of time in the first movement. Don't worry, I'll be much short. It'll be much. My exposition of the next two will be much briefer. But I just want to show you here. This is the sort of the ironic conclusion. Okay, that it says physics abandoned mechanicism, biology has embraced it at a close. This sort of strange situation. Okay, so let's get on now with the second act. The anti-reduction is sparked the trigger of the reduction revolution. So we go back to Bohr, okay? And why are we going back to Bohr's Light and Life? Well, because in the audience when Bohr was presenting was the very young Max Delbruck, theoretical physicist in his mid-20s, who was so struck by this idea of complementarity that he, said this many times after in his own accounts. Basically, this event changed his career. He decided to become a biologist as a consequence of being excited to find a complementarity relation in biology. And so he actually, Delbruck, one of his motivations for getting interested in biology is the expectation that a paradox, this is Delbruck's term, would emerge in biology that would be similar to the one that Bohr had solved for physics in 1913 with his model of the atom. Okay, so again, a very clear connection with developments in physics. So if Bohr was right and life was not reducible to physics, that's of course presented in the in Light and Life. Delbruck thought that the rigorous pursuit of a reductionistic approach would eventually, if pushed to its limits, would reveal some sort of problem, some sort of paradox that would require us to adopt this complementarity argument. Okay, if we go as far as hardcore as possible in a simple system and take it as far as we can, the expectation is that we would see the need for a complementary relation. Okay? And so that's what Bohr basically did. And here is him describing it in a little bit more detail. This is in an address, well-known address. Notice that he considered to call himself a physicist. Never, even 20 years later, he has another paper where he says a physicist looks at biology 20 years later. Even though he was in a biological environment, he always thought himself as a physicist. And here he's saying, very basically following on from Bohr's idea that it may turn out that something in the living cell, maybe even replication, stands in a mutually exclusive relationship to the application of quantum mechanics, and that a new concept of conceptual language has to be developed to embrace this solution. This should be taken as an opportunity, an open door for fresh views. Okay, and again, this is something that similar in some ways to some of the pronouncements that I mentioned already. And what happened, of course, is that Schrödinger published this very, very famous, influential book, What is Life? And in the book, it's a short book, this is the contents page, actually 3 of the chapters are discussing Delbruck. So Delbruck became well known through the discussion that Schrödinger offered of one of his papers, the so-called 3-man paper, 1935, that is this one. Okay, so this is a paper on the nature of gene mutation and gene structure, which Delbruck co-authored with Timo Petrosovsky and Paul Zimmer. And the point is that I won't get into the argument of what is life, but basically what Schrödinger takes from this paper from 1935 is the idea that we can provide a quantum mechanical model of what genes are. Okay, so we can think of the gene, following Delbruck, as a well-ordered association of atoms which are grouped together by solidifying covalent bonds in different configurations. And we can also explain mutation, because what is mutation from a quantum level perspective? It's simply the spontaneous transition of the system to an alternative alternatively stable isomeric configuration, right? It's it's a rare event, but it can happen. So it basically, Schrödinger, as part of his argument, takes this idea from that paper. In fact, he says at one point, if the Delbruck picture of the gene should fail, we will have to give up further attempts. This book influenced everybody with almost no exception. Okay, and so many young physicists and biologists decided to come to work with Delbruck after having read What is Life? And Delbruck, I'm not going to, it's a long story, but basically developed a whole, basically a group, a phage group, which worked with bacteriophage rather than Drosophila, because it was focusing on gene replication within the simple model. And with people like Salvador Luria, Alfred Hershey, and others developed this group, which he says at one point was imitating the Copenhagen spirit in physics, right? He's trying to think of again here of how of what it can take from Bohr. And he had these very famous annual summer courses at Cold Spring Harbor Laboratory that brought a lot of people together. And also in the continent, François Jacob and Jacques Monod and Andrew Wolff and of course James Watson, who came to work with Luria. They did a number of interesting. They applied new standards, rigor, and they made important developments in bacterial. I don't have time to discuss it, but the point is that even though, in a way, the phage group was a success because it's considered to be one of the important sort of building blocks of the story of molecular biology, the search for a paradox that had triggered the whole thing was a failure. There was never a paradox, never found a paradox. That's just something that didn't happen. In fact, already, even before the elucidation of the double helical structure of DNA by Watson and Crick, already by 1950, Delbruck was thinking that there was not going to be any paradox, and he actually abandoned phage research to study sense perception in a fungus. And when the double helical structure was presented here, again, you find Delbruck writing to Bohr and drawing another analogy with the physical development, similar to what Rutherford did in 1911. But eventually Delbruck admitted that the double helix had solved the mysteries of genetics, the very thing that he had wanted to do after listening to Bohr, in terms of classical models and theories without forcing us to abandon our intuitive notions of truth and reality, as in the new physics. Okay, so Delbruck himself recognizing that the new biology did not need the new physics. It was, H bonds and good old biochemistry, which Delbruck was very unhappy with, that actually helped sort of solve those sort of problems. If you look at the Fesch script, for example, that was prepared for Delbruck, Gunther Stedt, one of his students, the introduction of the whole thing is called Waiting for the Paradox. Of course, the paradox never came. And the really interesting thing is that even though for him, Bohr's complementarity principle was super important, it wasn't for any of the other members of the phage group, with one exception, the exception of Gunther Stedt himself, right? So, different members of this group at different points, right, have said, well, Bohr's view, Luria thought Bohr's view were tainted with idealism. Hershey never liked the complementarity double talk. Benson and Watson denied ever being influenced by Bohr's ideas. So basically, this is sense that even within the phage group, okay, it was just Delbruck romantically thinking in a way that essentially was irrelevant to the conclusion. Gunther Stedt is the one exception, but even he at some point said that he didn't really understand what Bohr meant by this notion. So again, it seems like the whole idea of complementarity was really of little use. If you think about the notion of the cell and of order that you have in molecular biology, what you really find is that the person who really influenced molecular biology was not really Delbruck, but Schrödinger in terms of the ontology. Schrödinger did not share Delbruck's enthusiasm for Bohr's complementarity. Of course, he was opposed to the whole Copenhagen interpretation. If you look at Schrödinger, also uses quantum mechanics in his book, but he's using quantum mechanics to solve a different kind of problem, which is the problem of stability. He thinks that the only way to explain the stability of macromolecules, right, they need to be stable enough to code information, even though he didn't use that language, is for them to be secured by the Keitel-London covalent bonds that are provided by quantum mechanics. Only with these solidifying bonds can molecules be what he called crystals, can be crystalline and rigid enough, right, to code for information. Okay, so there's a very different kind of appeal to quantum mechanics. So that's why he talks about the aperiodic crystal as being the structure of the genetic material. Remember that he's talking before DNA was increasingly identified as the carrier of genetic information, and a decade before Watson and Crick. And he also uses this language of a code script that specifies and determines the developmental process. It's a deterministic notion, like a genetic program. In fact, it's the forerunner of the genetic program in many ways. Okay, so you've got a very, very different view, because it's a view that is harking back to all mechanicism. Right, even this is the conclusion of Schrodinger's book, where he talks about the fact that the clue to understanding life is that it's based on pure mechanism, clockwork, which also hinges upon a solid, largely withdrawn from the disordered heat motion. Only by being a solid, by being a sort of crystal, can it be stable enough to not be disrupted by thermal agitation. And here is an example of how Schrödinger is very much committed to an old-fashioned 19th century explicitly Laplacian view, deterministic view. He says that when in using the term chromosome, code script to talk about what's going on in genetics, I really mean the Laplace systema. I really mean that in that genetic material, that it's sufficient to specify if the fertilized egg from the structure alone is going to develop into a hen or a fly or a maize plant or whatever. Okay. He also invests this code script, the chromosome, with agency. Okay, so this is again is a forerunner to problematic notions in developmental biology, right? DNA does nothing alone, but here you have Schrödinger already talking about the genetic material being not just low code, but also executive power, not just architect's plan, not just blueprint, but build this craft. And by the way, when Jacob and Monod coined the genetic program notion in 1961, they used almost exactly this formulation. Yeah, so I just want to finish this part just by drawing your attention to a review of the first script that I mentioned before by Dick Lewontin, that was actually published in, I think, in one of the first issues in the Journal of History of Biology, where he actually says that, telling the story, he's a critical review, and at the end he says, ironically, molecular biology originating in the hope of a paradox and a revolution ends up by being utterly mechanistic and the greatest triumph of the bit machine that Descartes could have possibly had. So that's my second ironic conclusion. Molecular biology arose in the search of a paradox that was never found. I'm mindful of the time, so let me just very quickly give you a sketch of my third act, okay, in which we are returning one last time to Bohr again. Why? Well, because the Lies and Life address was actually a product of discussions that Bohr had with one of his proteges, Pascual Jordan, who's actually based in Göttingen and maybe known for his work in matrix mechanics. He didn't win the Nobel Prize, but he was a student of Max Born and worked with Born and Heisenberg. But he had a long-standing interest in biology. And what's kind of interesting is that already in the late 20s, Jordan is thinking that this new interpretation of physics is going to be of help in biology. It's going to be able to help us understand certain aspects of biology, not just biology, but also psychology. There's a very big difference with Bohr, okay? Because what Bohr is doing in Light and Life, remember, is saying, look, this is an analogous situation. Just as in physics, you've got this epistemic situation where you need these two descriptions. In biology, you need that too. Jordan is saying, no, there's no analogy. Quantum mechanics itself, the phenomena of quantum mechanics themselves, ground the things that are most distinctive about organisms and also ground free will, ultimately, it's going to say. Okay, free will is a consequence of quantum mechanics. He actually works with both Bert Langley and Meyer-Abig, so there's a connection with the first act. I don't have time to talk about it, but very interesting. And in 1932, he writes this paper, Quantum Mechanics and the Basic Foundations of Biology and Psychology, 1932, just a few months after Light and Life, where he's basically saying that begins, of course, by talking about how we have an indeterministic view of nature now, given the recent developments in physics, and that this gives us reasons for optimism to overthrow determinism in biology. He even develops a whole theory called the amplifier theory, where he argues that organisms act as amplifiers of quantum effects. Organisms essentially are magnifying at the microscopic level indeterminate processes at the microscopic level, and that's how you have sort of the visibility of indeterminism at the microscopic level. A bit like a Geiger count. It's essentially an analogy that he draws himself. So he has this whole theory of the organism, of course, very speculative, not based on any facts, okay, but a way of using the new physics again to deal with how we make sense of teleology, how we make sense of the spontaneous creativity of organisms. Well, maybe all of it has a foundation in physics, okay? And the really interesting thing again is that actually Schrodinger's interest in biology was very much motivated, or it was triggered by reading this work from Jordan. So Schrodinger's What is Life, the book was published in 1944, was based on a series of lectures presented in 43. But a decade earlier, you look at the archives, he was actually already appalled by what Jordan was doing, because of course Schrodinger was not accepting this indeterministic account of interpretation of quantum mechanics. And so he actually writes to other Viennese, the Pribram brothers, Carl and Hans known for having developed this Bavaria, which is very important in history of biology. I don't have time to talk about that. But the point is that he basically writes to them and encloses the paper by Jordan and says, what do you think? They reply, and they are also appalled. And they say, we're glad to have you on our side as a confederate in the struggle against occult forces. This is a physicist of biology saying, this is occultism. This is unacceptable. In fact, I should say Jordan's arguments were very, very controversial. Bohr didn't like it because Jordan was using Bohr's name to bring legitimacy on his view, and it was a different kind of interpretation. And there's been wonderful work showing how basically most of the members of the Vienna Circle were appalled by this use of quantum mechanics. There's a whole, I think, special issue in Americanus, basically with responses to Jordan. And one of the papers that they suggest that Schrodinger should read is this paper by H.J. Muller, an American geneticist, called The Gene as the Basis of Life. And I mention it because Muller is, to my mind at least, is the most ardent genetic reductionist of the early 20th century. There's no one like him. He's defending that he's a student of T.H. Morgan. He was actually won the Nobel Prize, only the second Nobel Prize in genetics, but he has this view of genes as agents that are self-replicating, that are fundamental to everything that the organism does. In fact, the very title of the paper tells you how he thinks about it. They're not just the carriers of heredity, they're the basis of life. Okay, and what I want to just quickly tell you is that this way of thinking about genes was the view that Schrodinger really was influenced by, okay, which did not represent the consensus of genes at the time. So he actually presents this address in 1933, why are atoms so small, which is actually then becomes part of the introductory chapter of What is Life. And here is his notebook. If you look at the papers that he was reading, here is Muller's What is Life, Muller's Genes, the Basis of Life. And to give you a taste of how he's thinking about genes, he's talking about genes as the repositories of everything that organisms do, as the loci of agency, as basically the basis of everything. And the reason why that's important is that, as I said before, people came to know about Delbruck's view through reading Schrodinger. And yet Schrodinger actually misinterpreted Delbruck quite badly. This has been shown quite nicely by people like Sloan about a decade ago. This is a paragraph taken from this is the penultimate paragraph, in fact, of the paper, where they're saying, look, according to many biologists, we've got this view that genes are fundamental, that we can actually reduce development and the organism to the individual genes. They are the starting points of everything that happens, okay? The cell dissolves into the ultimate units of life. This actually is, of course, the view of Muller, and it's also the view that Schrodinger defends. The really interesting thing is, and this is the problem, the reason why no one noticed is because this paper was published in Germany in a really obscure journal that folded up into 2 issues and no one had access to it, is that actually the final paragraph is this one, where they say, our ideas about the gene challenge this picture. Genes, they present the view of Muller to then criticize it at the end, and to say that actually we should not think of genes in this way. We should not think of genes as the starting points of development, right? In fact, the consensus at the time, I would say, was not one so reductionistic, right? So I show you this just to give you a sense again of the contingency, right? This book that ended up having so much of an influence was based on a very selective reading of the genetics of the time. It did not represent how people were thinking about genes necessarily. It actually was developed to respond to Jordan's outlandish proposals of quantum biology. I'm going to wrap up very soon. The book actually has a very short epilogue, only a couple of pages, and it's actually on free will. Determinism and free will. What's interesting about this epilogue is this one sentence towards the beginning, where Schrödinger in some way gives away why he's got into the trouble of writing about biology, where he basically says, to the physicist, I wish to emphasize that in my opinion, and contrary to the opinion upheld in some quarters, obviously referring to Jordan, I don't know by name, quantum indeterminacy plays no biologically relevant role in the activity. Again, there's a lot that's been written on what is life. There's tons of papers, but this is not something that people have noticed. Okay, the idea that the whole project of Schrödinger was in some way to respond to his colleague Pascual Jordan and basically say that that interpretation of quantum mechanics is not going to be the one that we need in biology. Instead, he provides this deterministic Laplacian one, which ends winning the day, ends being the one that being influential. So I have some funny quotes of how of the acrimony that existed between Schrödinger and some of the Copenhagen people. You know, this is of course correspondence, not written. You know, and Schrödinger responding, "Oh, just these damn Göttingen people, they're just using my beautiful wavy mechanics to compute the shit in it in matrix elements." So anyway, it's a lot of acrimony, which is relevant. Okay. Which is relevant. Schrödinger was in some way already by the 1930s marginalized. You know, the consensus view in physics was the Copenhagen. And so in some ways, what I've been thinking about when thinking about what is life is that his motivation for turning to biology was to find a way to salvage this old physics, this old mechanistic, deterministic view of classical physics that seems to have been undermined by the Copenhagen interpretation. Okay, so again, something that people haven't actually noticed or discussed in the literature. And he won. Okay, the debate between Jordan and Schrödinger, he actually provided this view of macromolecules as fixed solid state crystals, and it seems to have been the way in which molecular biologists came to study proteins, right? Not just DNA, but proteins can be thought of structurally independently of the context because they are also assumed to be rigid for them to function. And so, you know, the hypothesis that I've been thinking about is that the influence of Schrödinger's ideas granted biologists a license to basically forget about stochasticity, forget about determinism, and think about the whole system as a piece of clockwork. Okay, and that, incidentally, is the view that we have today, although it's increasingly challenged. Okay, this kind of view in when you think about differentiation, or this kind of view when you think about atoms. Okay? Deliberately, purposefully modeled after the diagrams of electronic engineering mechanical. This is not a coincidence. Okay, there's an ontological. It's not being spoken explicitly, but this is the way you learn to think about the cell if you train as a molecular biologist. Okay. Okay, I will skip this. I just have some evidence of Monod being influenced by Schrödinger, but I'm going to skip that. And oh, this is very funny. Bert Lampe actually tries to review the book. Here is for a newspaper, and he just can't understand it. Because of course Bert Lampe was thinking about life in this dynamic way, and so he hears of the aperiodic crystal and he draws it. This is from the review. And I think this can't be possibly right. What we need to think about the gene is some sort of system which has a sort of a power of exchange. And so he basically suggests, and this is in 1946, right, quite late, that this can't possibly be right. You can't have genes determining everything. Just have it here just to show you the incapacity to understand how it could possibly be that organization could be encoded in molecules. For people of his generation, that was just made no sense whatsoever. All right, so I'm done. This is my irony that in some way the physicists like Schrödinger have made it legitimate for biologists to disregard physical effects like stochasticity and determinacy, right? Just one slide for a coda, which is basically what situation do we find ourselves now? Well, I've written at length about the problems with this machine view. I've got a 20,000 word paper that Eduard mentioned, basically taking a lot of time and care and effort to review the scientific literature to show how in different areas of contemporary cell biology, we have challenges coming to that machine view, and that the machine view is maybe not going to survive, okay? So this suggests that maybe a return to the future, as in a return to the recognition of indeterminacy and stochasticity, maybe these things have to be reckoned after all. And the final thing I'll mention is the fact that quantum biology, after having been a taboo term for 70 years, is again now suddenly being discussed in editorials in Nature, because it turns out that in photosynthesis, for example, there seems to be evidence of tunneling or and things like this, right? So I'll just leave that there. And my final slide is this, with the moral of the tale. I just have 3 morals very quickly. For historians, there's still a lot to learn about organicism and even about the origins of molecular biology. The thing that people thought had been done to death by lots and lots of historians, there's nothing new to say about it. I think that's wrong. I hope I've shown that. For philosophers, I mean, we need to really rethink how we talk about that relationship between biology and physics. It's not just about reduction. I think the story I'm told provides a lot of food for thought here, but I also have to think about the difference between epistemological and logical considerations. And for biologists, I think that learning about the fact that there were options available, options on the table that were not taken, liberates you from the idea that the way you think about the cell, the way you're trained to think about it, is inevitable. It actually isn't inevitable. And I'll leave it there. Thanks so much for your patience. Sorry for going over.